So this is the final video of the stoichiometry unit, and it's going to be very similar to aqueous solutions. We're going to be talking specifically about your neutralization reactions, acid-base solution stoichiometry. So some terms I want you to be familiar with. The first lab that we did involving solutions where you were trying to determine the concentration of a solution, specifically the NaOH, is an example of volumetric analysis. We were trying to determine how much of the NaOH was actually present in our solution by titrating it with the known amount of KHP. Titration is one way you can do this. Using a burette, you are able to, in this example, titrate a volume of known solution, the titrant, into a solution being analyzed, the analyte. We actually flipped it because we knew what we were titrating with. We needed to determine the concentration of the titrant in our example. So acid-base solutions, both your analyte and your titrant will either be an acid or a base. Can't have two acids, can't have two bases, one or the other. Your equivalence point is when you have added exactly enough of the titrant to react with the analyte. When you have used up both reactants completely, they are both limiting. It's also known as the stoichiometric point. Indicators, like phenolphthalein, which we used in that lab, can be used to mark the equivalence point. You pick indicators based on the color change from acid to base forms that it will go through at a certain pH. And you want to make sure that that color change corresponds fairly closely to your equivalence point. When we see that color change, we are at the end point of our indicator. And again, there's a lot of different indicators you can choose from. You will get to do some more with this when we do acids and bases in the spring. And the indicator you choose needs to match closely with the equivalence point of what you are combining together. And so, as I said, you want that light pink color in this particular example. They're titrating NaOH is being used as a titrant to analyze the acidic sample below, and it can be done with this. However, you have to know exactly what the concentration is of NaOH, and that's what we were trying to figure out in our lab. So these stoic problems are going to look a lot like the aqueous solution stoics. I didn't even include the steps for this one because they're the same as the acid-base ones. If you're dealing with stoichiometry, you need a balanced equation. So we need to write a balanced equation between hydrochloric acid and sodium hydroxide combining together. That's going to make water in your salt. We need to see which reactants we can find moles for. We can't find moles for HCl. We're wanting to find out about HCl, and specifically we're wanting to find the volume of a 0.1 molar concentration of HCl. But we do have a volume and a molarity for NaOH. And we know we can find moles from volume and molarity. So I take my volume after converting it into liters, and multiply it by its molarity, and that gives me my moles. Both my concentration and my volume have 3 sig figs, so I want 0.00958 moles of NaOH. Because I don't know exactly how much HCl I neutralized, I can use stoichiometry and the amount of NaOH I had to determine the moles of hydrochloric acid that were neutralized. And because it's a 1-to-1 ratio, it would be the same as the NaOH. I want to find volume of my hydrochloric acid, and I have a molarity of my hydrochloric acid. And to find volume with molarity, I need moles, what I just calculated. So I can set up my equation so that I solve for volume by taking the moles and divide it by the molarity of my HCl solution. The moles cancel out. They both had 3 sig figs. So I would have needed 95.8 mils of the 0.1 molar hydrochloric acid to completely neutralize all of that NaOH. So I've got another example that's pretty similar to the one that you just saw, but this time we're solving for concentration. I do want you to notice that there are 2 OHs in your basic solution, the barium hydroxide. So when you balance your equation this time, you need to account for that by having a 2 in front of the HCl and a 2 as a coefficient in front of water. We can't find the moles of the barium hydroxide. We're trying to find the concentration of our barium hydroxide, but we do need moles and we need a volume to be able to find concentration. Well, we have the volume, so let's see if we can find our moles of barium hydroxide that were consumed. We do have a volume and a molarity for our hydrochloric acid, so we can use those two pieces to find the moles of HCl that were used in this reaction. And at that point, we can use stoichiometry to relate the moles of HCl to the moles of barium hydroxide. It won't be a 1-to-1 ratio this time because you needed 2 moles of HCl to be consumed for every 1 mole of barium hydroxide. This does give me my moles of BaOH2, and along with my volume, once I convert it to liters, I can find my molarity of my barium hydroxide solution, which was 0.0500 m, or 0.0500 moles per liter, or 5.00 times 10 to the negative second molarity. So our final example involves nitric acid and calcium hydroxide. We do have volumes and concentrations of both reactants, and we want to know how much water was made, and we also want to know what ions were present after the reaction is completed. So we'll write our balanced equation between nitric acid and calcium hydroxide. And because we have volume and concentration for both reactants, we need to determine which one is limiting by finding the moles of both of those quantities. So I take my volume, I take my molarity, and I get my moles for both HNO3 and for calcium hydroxide. They both had 3 sig figs for their volume and 3 sig figs for their molarity, so we needed 3 sig figs for their moles. We want to calculate the amount of water. You could calculate the amount of water in moles. I'm pretty sure I calculated it in grams because that's what you would actually measure in lab. But either one would be sufficient since I did not specify a unit. I'm going to take my moles of nitric acid, since that was the first one I calculated, and convert that to grams of water using my moles of HNO3 as my denominator so I can cancel them out. There's 1 mole of HNO3, or moles always gets 1, but then you multiply by the coefficient, so 1 times 2 would give you that 2 there. And then with grams of water, you need the molar mass, 18.02, as well as its coefficient 2. And if I do my math through, coefficients don't affect my sig figs, but my molar mass had 4 sig figs, my moles had 3, so I wanted 3 sig figs in my grams of water. I can do the same thing with calcium hydroxide. I take the moles of the calcium hydroxide. There's always going to be a 1 in front of moles, and there's also a coefficient of 1 in front of calcium hydroxide. So I just put the 1 there. The grams of water stays on top with 18.02 and its coefficient. And when I do the math through this time, I see that I made less water with the calcium hydroxide than I did with the nitric acid. So that is going to determine how much of the water I can actually make. I also want you to notice that it was calcium hydroxide that was my limiting reactant, which means all of the hydroxide that was consumed, or all the hydroxide that was present in the calcium hydroxide was completely consumed. So if I want to know what ions are present when the reaction goes to completion, I need to keep in mind that limiting and that excess reactant. The hydroxide is gone. It got used up completely. You would not expect to find any hydroxide ions in your mixture at this point in the reaction. Our spectator ions were diluted, but they should still be there in the same amounts that they were to begin with. So both nitrate and calcium should be present. And then the hydrogen ions that were part of the nitric acid were used somewhat, but they were not used completely, so they too are still present in my mixture.